Hi Judip, I'm Chandramouli, the TA for this course. So today we'll discuss some problems related to first law and second law of thermodynamics and some other small topics. Okay, so basically this week the course was taught mainly on problem solving. So the assignment problems are also related to whatever we have done till now for the past 6 weeks. So I have prepared a few questions which we can go through. So do you have any questions in particular that you would like to talk about?
Yes, sir. I have some problem on week 6 quiz part.
Okay, can you tell me
Can
the
you tell me the
questions?
questions?
Yes, sir. 7,
Okay, just a minute. Give me a moment. Go to the course. Okay,
Okay,
question
question
7,
7,
8,
then
then
8, okay,
8, okay,
11, 13,
11,
11,
okay,
okay,
13,
13,
15, and 4, 6.
15 and
15, and
4, 6.
4 or 6
4 or
as
6
well.
as well.
Okay, 4,
Okay, 4,
6.
6.
Okay,
Okay,
so
so
4,
4,
6,
6,
I'll, I
I
am
am
discussing some of
discussing
the
some of
problems
the
related to
problems
that.
related to that.
Then
Then
7, 8
7,
are
8 are
just theoretical problems.
problems.
I'll
I'll
talk about it.
talk about it.
11 as well.
11 as well.
And
And
13, yeah,
13, yeah,
13 also we
13
can
also we
discuss.
can discuss.
Okay,
Okay,
Yes, sir.
sure.
sure.
All right. So first, let me show my screen. So you're able to see my slides, right?
Yes, sir.
So, okay. So first problem, we'll go one by one. So as you can see, it's a PV diagram and we have a system. So the system goes from A, C, A to B via two paths. One is ACB and another is ADB. So these are the two paths that they have discussed. So just ignore the arrow mark. It's like written wrongly. It should be like this. Okay. Somebody has joined. Give me a moment. Submit. All right. So Satish, we have okay. I think this is left. Okay. Anyway, we'll continue. So basically it's the other way around. So first thing is you see that along path will first take the what they're given is path ACB, which is basically going like this. So A, can you see my cursor? A to C to B. Okay. So that's the first case. Okay. So, yeah, path ACB. Okay. So now what are they telling? So in path ACB, path ACB, the heat flow into the system, so it's a positive quantity, 84.4 kilojoules. Okay. And then the work done, system does work. So what is the sign for that? It was wrong. Jagdeep, what is the sign for when system does work? Sorry?
Negative, sir.
Okay, correct. So it is minus 31.65 kilojoules. So basically, we have two state points A and B. So one path is ACB. So now what are they asking us? They're asking us what is the heat flow into the system along path ADB if work is done. Okay, fine. First we'll calculate the change in internal energy. So what is the change in internal energy? from A to B? How will you get it? Change in internal energy is equal to what? Jaideep? It is Q1 plus W1. Okay. So that is the change in internal energy. So what is the value now? 84.4 minus 31.65. So therefore, change in internal energy when you go from A to B is just reversing. Okay. So that is 45, 3, 13, 13 and 6 minus 13 minus 6 is 7. And this is 3, 2, this is 4. Okay. 14, 4. Yeah. So this is the change in internal energy when you go from A to B. Now what we'll do is we'll go to second path. Path A, D, B. Okay. See, since internal energy is a state function, the delta UAB, irrespective of the path, will still remain the same. Okay, because it's a state function. Okay, state function. Doesn't matter whichever path it goes by, it just depends on the initial and final portion. Okay, so now what we'll see do is what they are asking us is what is the heat flow into the system along this path, second path, if work done by the system is 10.55 kilojoules. So now for this path, it's again I'll write it as Q2 plus W2 is equal to 52.75. So now W2, what they've given is minus 10.55 kilojoules, correct? So minus 10.55 kilojoules is equal to 52.75 kilojoules. So therefore, the heat flow along this path will be just addition of this, which is, sorry, 10, 12, 13, 13, 3, 6. So this is the answer. All right. So that is the heat flow along this path. Okay. Do you understand?
Yes, sir.
Okay. So it's quite simple. Okay. The main concept over here is internal energy is a state function. So whichever path it goes, the change in internal energy between A and B is going to be the same. So one path they have already given the work done on the heat, or the other path they have given the work done. So you just need to calculate the heat. So it's quite straightforward. Now, second question is actually a continuation of this thing. So as you can see here, what they're giving is internal energy at A, first point is 0. Okay. And then internal energy at second point D along path ABD, it's 42.2 kilojoules. Correct. So let's see. So they're saying here internal energy is 0 at point A, at point D it's 42.2, and then at B. So what they are asking us is what is the heat flow along this path AD and BD. So can you tell me how it will be? Can you tell me how we can calculate? Think about it and tell me. Okay. What is the, so this is 0, okay? What is the delta U what is the delta U for A to B? We are already calculated that. What is the value? Can you tell? See here and tell.
84.4.
No, that is the heat. Delta
Uh,
AB is
the
52 point, delta UAB is,
52.75.
yeah, okay.
52.75.
So let's say this point is 0, then what is the internal energy at this point then? At point B. This is 0 and delta UAB is 52.75. So what is the value at B?
57.75.
Same, right? 52.75, correct?
Yes, sir.
Because it's 0 and delta U is the entire internal energy change that's going to happen here. So now, internal energy at point D is 42.2, okay? So this point it's 42.2 and B is 52.75, all right? So
Yes.
between B and D, what path is this? Can you tell me something based on the PV graph? BD, see the path. What is not changing here between B and D point? From the PV graph, which is not changing between B and D?
V is not changing.
So V is not changing. So if delta V is 0, then what is the work done? What is the work done formula?
Delta U.
No, work done, work done. PdV, right? P into
PdV.
delta V, change in volume, external pressure into change in external volume, right? Change in volume, sorry.
Yes, sir.
So since delta V from this path, BD path is 0, there is no work done in this phase, all right? So if there is no work done, then all the change in internal energy is going to come from the heat flow, because change in internal energy is heat flow plus work done, correct? So if W is 0, work done is 0, then all the heat is going to come from your heat absorbed, okay? So we'll do that. So we know UB, right? Yeah. We know UB is equal to, wait, UA, we know from first UB minus UA is equal to delta UAB, which is UB minus 0 is equal to 52.75. So therefore, UB is equal to 52.75 kilojoules. So this part we are clear. So the next thing is path BD, path DB, or sorry, path BD is isochoric. So that means no volume change, which implies no work done along that path. So which again implies delta U BD is going to be equal to the heat flow into the system. So what is delta UBD? UB minus UD. Sorry, final is D, right? UD yeah, UD minus UA, which is QBD. So we know UD value, that is already given 42.2. So this is 42.2 minus 52.75 is equal to QBD. And this is going to be negative because they're asking heat absorbed, correct? When heat is absorbed, right? Yeah, if heat is absorbed, then it's going to be negative. Let's see. sorry, heat is absorbed, it's going to be positive. Now I'll come to it. Correct. First we'll do the arithmetic. And 5, 4, sorry, going 5, 5, 5, 0. And yeah. So this is heat is being released. But what we see from graph is PD, no? Yeah. What we see from graph is path is like this, okay? This is the reverse. So when you're going like this, heat is going to be absorbed. But when you're coming back, heat is going to be released. So now we need to get the QdV. So that is the absorbed part. Along path ADB, QdB is what we want. So that is kilojoules. So this is one heat absorbed that we got. Now we need the next parts. What is the second one? Second is what is the heat absorbed along AD? This path. This path is something that we want. Okay. So tell me how we can calculate this. Think about it and let me know. Is work being done over there?
Here pressure is constant.
Huh? And then is work being done over there?
Yes, sir.
Work is being done, right?
Yes, sir.
Okay. So how much will the work be? Or can we calculate it? Oh, sorry. Change this first. Work is being done. So how can we get the work done? Think about it and tell me. Okay, Jyoti. So, from the first question, what did they tell? The work done along path ADB is 10.55 kilojoules, correct?
Yes, sir.
Okay, so there are two steps here, A to D and then B to D. What is the work done
Yes.
along D to B?
No.
No work done.
Zero.
So that is 0.
Yes,
So
sir.
the entire work must be done in this step, right? A to D, correct?
Yes, sir.
Huh. So if entire work done is done in this system, in this path, so what is the work done now? It's already given, right?
Yes, sir. 10.5.
10.55, correct? So that is the work done along AD path. So we'll come to path AD. In path AD, work done is equal to 10.55. That is okay. That is negative because work is done by the system. Okay. So now delta U AD is UD minus UA. UD is what is it? What is this, the value that they have given? They have given 42.2 kilojoules for D. Correct. So that is 42.2 minus 0. So therefore delta UAD is equal to 42.2 kilojoules. So now what is the formula for delta UAD? How can you separate it as heat and work done? QAD plus WAD
Ready.
is equal to 42 point, correct? So we know the value for this minus 10 point, so which implies, so we just push this little bit up, create more space. So QAD is equal to 42.2 minus WAD. So we know W is minus 10.5, so minus and minus plus. So 42.2 plus 10.55. Therefore, heat flow in this path is going to be 75 and 52 kilojoules. Correct?
Yes.
So these are the two workflows. All right. So do you understand this part?
Yes, sir.
All right. So next question. Actually, you should tell me quickly because read the question and tell me how we can solve the problem. Okay? Because it's quite straightforward. I'm pretty sure you know the answer. How can we solve, Jiggy? Tell. Tell me what and all do we have from this graph? Jiggy, are you there?
Sir, can you tell me
Sorry, can I tell what?
another time what you tell?
Jiggy, I can't hear you properly. What are you telling?
Sir, can you ask me again what you tell?
No, what I'm asking is you read the problem and tell me how we can find the temperature at points 1, 2, and 3. You can see the graph, right? P and V.
Yes,
Huh.
yes.
So So I'm pretty sure you know the answer for this. You can tell me how we can go about finding the temperatures at point 1, 2, and 3. Okay, so tell me what are the things we know from the graph. You first let's summarize it. What are the things that are present? What is the pressure at point 1?
One is pressure,
1 atmosphere, right? Okay.
one atmosphere,
Okay. Pressure at point 2?
0.5.
No, no, point 2. See, where is point 2? Point 2
Yeah,
is here.
one,
Again 1 atmosphere. What is pressure at point 3?
0.5.
Yeah. Okay. So we have these three pressures. Okay. So now what are the things? So what is the volume 1? Volume at point 1.
22.44.
Okay, 22.4 decimeter cube. Okay. So volume 2 is
44.88.
that is also equal to volume 3, which is 44.88. Okay. So we have these three things. So then what are so how many moles of ideal gas?
One
Sorry, 1 mole, right? So N is equal to 1. Okay. So what are they asking us to find? T1,
T
T2, and
T3.
T3 is what we want. So how can we find this? Now, can you tell me the formula that we can use to find these? Think about it and tell me. What formula? What is the ideal gas formula? What is the ideal gas formula? Ideal gas equation?
PV
What is the
is
ideal?
equal to nRT.
Yeah. Okay. So
Sir, here we
P,
can use PV by NR.
huh. So we know P, we know N, we know R, we just need to find out one temperature, correct? So
Yes,
we'll find out for okay. So we need the correct value for R. So as you can see here, it is in decimeter cube, which is actually 1 decimeter cube is equal to 1 liter. So and it is an atmosphere. So we need the correct value of P. Sorry, R. So I have already noted that down. So the value is 0.082, okay, liter atmosphere per Kelvin per mole. Okay. Note that 1 decimeter cube is equal to 1 liter. So those two are equal. So we don't have to worry about that. So this is the correct R value that we are going to use in this calculation. Okay, it's quite straightforward. So what is the first point one? One. What is the so P1 V1 is equal to NR T1. So simplifies T1 is equal to P1 V1 by NR. So simple. So that's what we are going to use. So what is P1? 1 atmosphere. V1 is 22.44. Decimeter cube is equal to liter. So then 0.0821 and N is 1 mole, right? So this is liter, atmosphere, Kelvin, and mole minus into 1 mole. N is 1. And this. So now mole and mole will get cancelled. Atmosphere, atmosphere, liter, liter. So we have k minus 1, k to the power minus 1 in the denominator, which will go above. So we'll get the correct units. So that way we don't have to worry about units. So we just have to calculate the, I'll just later get the calculator. What do you want? We want 22.44 divided by 0.0821, which is 273. We'll just keep it as 273 Kelvin. Okay. So T1 is equal to 273 Kelvin. So first point, we know the temperature. Right? Just a minute. I'm joined here. Check, joined. No worry. Weird. Anyway, so this is first point. So next is second point. And 2 is, again, we can write the same formula. P2, V2, sorry, I'll just directly write temperature. T2 is equal to P2, V2 by NR. I'll not write the units now, so because we already know. What is P2 value? P2 is 1 atmosphere, V2 is 44.88. So it's basically double. 1 into 44.88 divided by 0.0821 into 1. So this is quite straightforward because it's just the double. So I'll 7546 Kelvin. And then we have 0.3. So can you tell me the formula for 0.3? You can, you can quickly do the value. Tell me the value for 0.3. 0.3. So T3 again P3 V3 by NR, right? So what is the value for P3? 0.5, correct? 44.88 divided by 1 into 0. So therefore T3 is equal to, it's going to be 273 Kelvin. Fine. It's pretty straightforward. Do you understand?
Yes.
Okay. Do you have any doubts?
No, sir.
Okay. So the fourth question is about how to calculate the Joule-Thomson coefficient. So what is the Joule-Thomson coefficient formula? It's just application of formula. What is the formula for that? Nu Jt is equal to what? 1 by Cp del H by del P at a constant temperature. So this is the formula. So we have del H by del P by T value and Cp value. So it's just simple substitution and then we'll get the value. Minus 1 by, what is this? 110 joules Kelvin per mole. 2 minus 3.29 into 10 power 3 joules. Pascal minus 1, mole minus 1. So this joules, joule will get cancelled, mole will get cancelled. So Kelvin will come up. So then negative and negative are there. Let's just remove that. 3.29. Negative into negative is positive by 110. Kelvin will come up. So Kelvin megapascal megapascal. Okay. So let's just do the arithmetic now.
90.
Sorry, how much?
29.9.
Okay, 29.9. Good. All right. So that's the answer. So this is Joule's Thomson coefficient for a real gas. So what is the Joule Thomson coefficient for an ideal gas? It's pretty straightforward. Or Joule's coefficient for an ideal gas, what is it? It's zero, okay? Joule's coefficient for an ideal gas or Joule's Thomson coefficient for an ideal gas, it's zero. You check the notes, you will,
Actually, in first sem in
yeah,
syllabus,
yeah.
actually we did not study in that because in first sem our syllabus has not this
Oh,
topic
okay.
has our syllabus in first sem.
Oh, okay, okay. But sir actually taught this in the lecture video, right? I think third week.
Yeah,
You didn't
yeah,
go
yeah.
through the lectures? Did you not go through the lectures?
Yes, sir.
Okay, okay. You go through the lectures. Actually, these are there in the lectures. So I think sir taught us. So you can just follow that. Yeah, I know. In first semester, you may not have this. This is, I think, it's like third semester
Third
subject or
semester,
something.
yes, sir.
Yeah, yeah, third semester subject. Correct. Okay, so we have question 5 now. So what are they asking? Calculate the change in entropy involved in heating a gram atomic weight of silver at constant volume from 273 Kelvin to 303 Kelvin. And they're given the CV. So what is the formula for change in entropy? For a small change in entropy? What is it? By definition, what is the change? Ts is equal to what? dq, reversible path by t, right? So this is by definition. Okay. So in a constant volume process, see, they have given it's a constant volume. Okay. So in a constant volume process, dq, constant volume process is a reversible process. It's equal to cv dt. All right. Fine. So this part is clear, right? So now ds can be written as what can, I mean, it will be written as what? cv dt by t. So now to get the change in entropy, you integrate both sides. So if you integrate, what do you get? So T1 to T2 CV dt by T. So CV is constant, we'll take it out and we'll, for now, we'll keep it as T1, T2, okay? dt by T, right? So what is delta S now? Alright, go to the second page. So what is delta S now? What is this integral? So
T2 by T1.
this integral, what is it?
T2 minus T1.
No, that is only
Uh,
dt.
T, T2 by T1.
What? Natural log, right?
Yes, sir. Yes.
Huh.
T2 by
So it
T1.
is cv ln t2 by t1. So in our problem, so t2 is 303, this is 273. So we'll just put those values. So what is the cv value? cv value is 5.85 calorie kilo. Okay, 5.85 5.85. It is T2 303 by 273. So therefore, delta S is equal to, just do the calculation. Ln is
0.609.
0.609. Okay. Let me just do this. Ln of this. Okay, what have I done? Sorry. What have I done? 273 ln. What am I doing? 73 ln into 5.8. Oh, sorry. Then ln into 5.8. Okay, so this is 0.61. We'll write it as a calorie per Kelvin. Mole, no? Since it's a gram atomic, we'll keep n, the number of moles will be here. So it is mole will be gone. So this is the final value. And if we go about, we have that option as well. So this is the option. B is the option. Okay. Fine. So you're clear with this, right? Till now?
Yes, sir.
Okay. You have any doubts?
Sir.
Okay. So this problem, so we have delta. Okay, so we consider a system where it is undergoing an isobaric process and temperature is at 300 Kelvin, which is given. Okay, and then we have the delta S of the system, that is minus 100 joules per Kelvin. And then they have given the enthalpy change of the system, which is minus 200 kilojoules. That means, enthalpy is basically decrease. The enthalpy of the system is decreasing, and they're asking us to calculate the delta S universe. Can you tell me how we can go about this problem? We want delta S universe, right? So what is delta S universe? Delta S system plus what? Plus delta S surroundings. Correct? So this you're clear, na? Because
Yes,
system is
sir.
there, everything else put together is going to be the universe. So now delta S system is already given, so we don't have to worry about that. We need to calculate the delta S surrounding. So delta S surrounding, what is it going to be? The heat change of the surrounding, how much heat the surrounding is getting, correct? dq reversible by T. Okay, let me just put this delta Q. All right. So if you see here, they have given us enthalpy change of the system. So what we are going to assume is delta H of the system, the enthalpy change, it's entirely going to be converted into heat, and that is going into the surroundings. So basically, the delta Q of the surrounding is going to be equal to delta H of the system, because it's negative, right? Negative means it's releasing, correct? So since it's releasing, so for the system it's negative, but for the surrounding it's going to be positive. Are you clear with this point? Why I'm changing the sign from negative to positive? Because okay, I'll just put it as, yeah. Okay, this point is clear for you now.
Sir, can you explain again?
So what we are going to say is this change in enthalpy of the system, okay, change in enthalpy of the system, change in enthalpy of the system, enthalpy of the system is released into surroundings as heat. Okay, since this since delta H system you see is negative, that is for the system it's negative. That means what? It's releasing into the surroundings, correct? The heat is going away from the system. If it's going away from the system, for the surrounding, it is coming into the surrounding. So that means it is positive. So that's why I have put delta Q surrounding is negative of delta H system. That's why negative and negative is going to become positive. You understand?
Yes, sir. Yes, sir.
Okay. So in that case, we have delta Q, we have temperature also. So delta S surrounding is equal to 200 kilojoules to 10, I'll just put it as 10 power 3 joules, okay? Divided by, what is the temperature? 300 Kelvin, correct? Let's cancel these zeros. So if we do this, what's it going to be? So is this. Okay.
Refill 6.66.
666, huh? It's 200 kilojoules. Hmm? See, okay. 666.67. What is the value? Joules per Kelvin. Okay. So that is the delta S surrounding. Okay. Now delta S universe. That is equal to, what is the delta S system? Delta S system is minus 100. Okay. Minus 100 joules per Kelvin plus 666.67 again joules per. So what is the total value now?
566.66. 67.
Correct. Equal to 566.67. So delta S universe is positive, which is correct, right? For a process to occur, for a spontaneous process to occur, for any process to occur, the delta S universe should be positive. It cannot be negative.
Yes, sir.
But for system it can be negative, such that for surrounding it's more positive, right? So since even though system is negative, surrounding is making up for the decrease in entropy inside the system. So total delta S universe is positive. So that way it's possible. Okay. Now we have another question. Yeah, this is something that you wanted, right? We'll discuss this. Okay. So this is a PV diagram. Okay. PV diagram. They're asking, this is an ideal gas. They're asking what is the total work done in going from state 1 to 2. Okay, so can you tell me the work done formula? Huh? What is the work done formula in general? Here as well. What is the work done formula, JD? Minus what? JD?
Yes, sir.
Minus P what? Into delta V, right?
Yes, sir.
Okay. So you have a PV graph. Okay. P value you have. Okay. And what is delta V? It is the difference between any 2 points in the x-axis, correct? Let's say it's
Yes,
5
sir.
here, it is 1 here. So it is 5 to 1 is, that's the delta V. 5 minus 1 is the delta V. So basically from the graph itself, we can find out. So I'll just do one more thing. This is the point here. This point I'll keep as A. Now, so tell me how we can find the A work done here from this graph. For first, tell me the work done for path 1 to A. For 1 to A, what is the work done? Can you tell me that? What is the delta V here? Minus P1, first point. What is the
Sir, yeah,
delta V here?
0,
Ha, so
0,
it is 0. So delta V 0. So what is this?
0.
Work done is 0. Okay, fine. First thing we did. So next is A, point A to 2. So now you tell me the value here. Work done A to 2 is equal to minus P2, because pressure is constant, right?
That's
Constant
right.
external pressure, and delta V. So delta V now minus P2. Okay, P2 value. Can you tell the P2 value?
2, 2.
2. Okay. Now what is the delta V? We are going from what to
5
what?
minus 1.
No,
5
no.
minus 1.
What is the final volume? First we have to tell the
What
final volume.
is
1,
2,
right?
2, 2. 1 minus 5.
1 minus 5. Correct.
10, 8.
Yeah, that's all. So simple, right? When you have a PV graph, you find the area under the curve, you'll get the work done. So 8 some units. So now the total work done in going from 1 to 2 point is work done 1 to A plus work done A to 2. Correct? First, this is 0. This is 0. So therefore work done 1 to 2 is equal to 8 units. Fine. You understand this?
Yes, sir.
Simple, right? Yeah. Okay. So now we are done with this. Can go to the next question. Okay. Now, okay. Now this is a little tricky problem, but we can still do it. So what are the things? Okay, first you read the question and tell me what are the things that we can understand from what did you understand? You tell me that first. You read the question and tell me. What are they telling? It is first, what are the key points here? Expansion, huh? Okay. Adiabatic, quasi-static,
Expansion.
huh? So what are the things here? So what does this mean? All these means to what? Reversible. Quasi-static means, you can consider it as very slowly happening. So it's kind of reversible. So basically reversible, adiabatic, expansion, and they are giving us something. They're telling us PV to the power gamma is constant. All right. So this is the main important thing that we need to find out. Okay. So since I'll just draw a small graph. Uh, yeah. PV, let's say this is adiabatic expansion. since it's an expansion, pressure is going to decrease. Let's say it's an adiabatic expansion. It's going like this. Okay. So this is P1, PI, VI. Then this is PF, VF. And along this path, it could be any P, any V. All right. So what do we want? They are asking us to calculate the work change in this thing. Basically, we need to find the area under the graph, but we cannot do it directly. So work done, as we know, simple. We'll start from scratch. Minus PD, correct? So this is dW, correct? This is fine. Basic formula. So if you want work done, what are we going to do? Since it's like area under the curve, what is the thing that we want to, what do we do? Integrate, right?
Yes, sir.
Okay, so that's what we'll do. Minus P dV integrate. So from VI to V, oh, let me write it a little bit below. Okay, work done is equal to minus P VI VF P dV, correct? So important thing is here P is not a constant value. Okay, so we cannot take it out. It is going to vary with the volume. So since it's going to vary with the volume, we need to find P in terms of the some constant values. So we know the initial point. Initial point is PIVI, correct? Initial point to PFVF. So now you take any arbitrary point within that path, we'll call it as P and V. Okay, gamma is going to be equal to PI VI to the power gamma. So this is what is given in the problem. So what we'll do is we'll write P as known values. Pi is known, Vi is known, divided by V power gamma. So this is our new P value. So we'll substitute this in the integral and we'll take it from there. So minus, we can take it outside, Vi, Vf, Pi, Vi, gamma, divided by V gamma. Here, if you see, P and V are knowns, so they are going to be constants, right? So we can take them out. So I'll take it out of the integral. But V, it's a variable. It's not a constant value. So 1 by V power gamma dV. So what is the integral for this value? Jerry? What is the integral for this value? V. Tell me the integral. V to the power what? It is basically it's minus is the value plus 1, right? So this is the integral, correct? We add to the power. We add 1 to the power, correct? So this is Vi to Vf. So this is what we have. So what I'll do is I'll just change it up. What I'll do is minus Pi Vi divided by, I'll just write it as 1 minus gamma. Alright, so then it becomes Vf 1 minus gamma minus Pi 1 minus gamma. Okay, so let's create some space here. So let's multiply this. Okay, let me just multiply this. I'll keep 1 minus gamma also minus, okay, if I multiply this, minus pi vi, okay, vi into vf 1 minus gamma minus and minus plus, correct? So pi, then we have vi 1 minus gamma, correct? Oh, sorry, I missed something here. I missed the gamma here, correct? When I took it out, I missed the gamma. Gamma power, gamma power. Yeah, the power gamma. There are two things. So what is this value? Jaydeep? Vi to the power gamma, vi 1 minus gamma. So this will just be vi to the power 1, right?
Yes, sir. Yeah, it will be.
So similarly, pi vi to the power gamma is equal to pf vf to the power gamma. So this is already given. So we know 1 by 1 minus gamma. This is going to be minus pf vf vf 1 power gamma 1. So this is gamma again plus pi vi. So this is quite straightforward. So then create some more space. One by minus gamma. It's going to be pf. Sorry, this. I'll keep positive to the left side. Pi vi minus pf vf. Okay. So now we have work done. So I'll just rewrite it a little bit so that it's the same as some of the option, one of the option in the answer. Yeah. So it was vi minus pf vf by 1 minus gamma. So this is the final answer that we have. Okay. Okay, I did a mistake here. Sorry, I did a mistake here. Also, I was checking. I didn't take the negative inside, but I have taken the negative inside. Sorry. My fault. Should be, you see, I just did a mistake here. So I'm just correcting it. It's just a sign mistake. Something that I do a lot of times. Yes. Okay. So PF VF will remain the same minus PI VI. Yeah. So then I have just rewritten it so that it resembles the answer in the option. Okay. So this is the final answer. Do you understand this part or you have some doubts here?
No, sir, understand.
Okay, good. So now one more question, then I'll clear some of your questions from the assignments. There are, okay, so this part, okay, so what do we have here? We have two blocks of metal, okay, same actually. So same mass, same temperature, okay, same mass, same temperature, sorry, different temperature. T1, mass is, I'll keep it as, right. So same mass, same mass and same material, so Cv is the same. Then it is temperature is this. In second block is T2, mass is same and Cv is same. So they are brought together. So now what we'll do is let us assume let's not assume we need not assume it. So when they are brought together, there'll be heat transfer between these two blocks and their temperature will become equal. So what we'll do is let final temperature be Tf. Temperature be Tf. So whatever heat is going from the heat change that is happening in block 1 will be equal to the heat gained by block 2. Okay, so we'll assume T1 is greater than T2. Let T1 be greater than T2. So in that case, the heat lost from dq1 will be equal to dq2. Heat lost is equal to heat gained. Okay, so what is the formula for this? Mass into Cv into change in temperature. Similarly, mass into Cv into change in temperature. I'll put it as T dash. So that is going to be equal to mass into Cv into what is the final temperature? Tf minus T1. Again the same here. Mass into Cv. Final temperature is Tf minus T2. Okay. So these are equal, so they'll be cancelled. So, okay. Change in temperature. It'll rise. No? Final temperature. Yeah. No. Which is heat lost? Minus. This is heat lost, so it has to be minus. Yeah. So since this is heat lost, I'm putting as minus. So then it is T1 minus Tf is equal to Tf minus T2. So 2Tf is equal to T1 plus T2. So which implies Tf is equal to T1 plus T2 by 2. So this is the final temperature. That's quite straightforward. Okay, it's quite simple. Even if it's different material, we can calculate the values. So we need the entropy change. So entropy change, as you know, again, ds is equal to dq reversible by t. Okay. Oh, sorry. Wait. We need different things. We need total entropy change. So delta S of the entire process is equal to first block, entropy change in the first block divided by entropy change in the second block. Okay. For the heat transfer thing, for the heat transfer, it is, since it's done at constant pressure, it is Cp. Right. Cp, I guess. Just a minute. Cp of Cp. Cpm. Yeah. Cp ln Tf by T initial, which is T1, plus Cp ln Tf by T initial, which is T2 here. So it's going to be Cp ln Tf into T1 plus ln Tf by T2. Okay. So since it's ln, you can just multiply, right? Multiply the values inside. So it will be Cp ln T. If you multiply Tf square divided by T1 into T2. Okay. So what is Tf value? T1 plus T2 by 2, right? So we just need to square it. So basically it's T1 plus T2 into whole square. 2 square is 4. So 4 T1 into T2. So this is the total entropy change of the process. All right. Do you understand this part? Jyoti?
Yes, sir.
Okay. So if that is there, then what I'll do is I will give me. Okay. If that is there, then we can discuss some of your doubts from the problems. So let's say I'll change the presentation. Okay. So, this. Just, yeah, you can see the tab, right? You were asking question. Which question you were asking? 4 and 6 we already discussed. Problem similar to that. 7 and 8, no? So 7, for a chemical reaction and gas phase at constant pressure and temperature, work has to be done by the system. Okay. So when does a system does work? When does a system do work? When the system expands, it does work, right? Correct?
Yes, sir.
So when will you get an expansion? When more number of gases are being formed, then the system is going to expand, correct?
Yes, sir.
So since it's a gas phase reaction, you need gas to be formed. So when the number of moles of the product is greater than the number of moles of the reactants, the system has to do work to expand. Okay?
Okay, sir.
Do you get this?
Yes, sir.
Jaideep?
Yes, sir.
Okay. So the second thing, 8 is for maximum work, all just remember this. Work done is maximum in the reversible path. So basically, you have to find the option that tells you that it is a reversible path. So basically, since they're telling that there is mechanical equilibrium with the surrounding at every stage of the process, which is basically the definition of your reversible path, the final option is the answer. So then, okay, you get that point?
Yes, sir.
Okay. Then question 11, what are they asking is, you're going from state 1 to 2, correct?
Yes, sir.
By path B. Sorry, through path A. Okay. From 1 to 2, they are going through A and then coming back through B. C is alternate path. What they're asking is, what is the change in enthalpy of the system if the system undergoes these different paths? So just tell me one thing. Enthalpy is a state function or a path function?
State.
It's a state function or a path function? Jaideep? Okay, what is state function? Jaideep?
Hello.
A property which depends on the initial and final points alone, right? Final states. So that is state function. Okay.
Yes, sir.
Path function depends on the path taken. It will be different for a reversible path or an irreversible path. So now tell me, enthalpy is a state function or a path function?
Enthalpy is a state function.
So since it's a state function, does it matter if it goes through path B or C? No, right?
Sir, yeah.
So basically, it just depends on the points 1 and 2, or if it comes back to 1, that's it. So it does not depend on the path taken. So whatever path you're taking, it's going to be the same.
Wow. Yes. Okay.
Okay. Now, what else did you ask? You asked question 15.
Yes, sir.
So again, so they're asking the total change in entropy for the process below, where it goes from 1 to 2
Enthalpy
to
is a
3.
state function, so here path is not.
Yeah, path, it's a state function, so path does not, it's not dependent on path. And also for a cyclical process, change in entropy is going to be 0, right?
Zero.
It's
Yes,
coming
sir.
back to the same point.
Yeah.
Yeah, that's all. Then one more thing. So here, this problem actually I can solve it and show, but I want you to do it yourself. So what is the main in an engine? What is the main relation? T1 by T2 should be equal to Q1 by Q2, correct?
Yes, sir.
So use that equation and see if this is working on, correct?
Okay, sir.
Okay. So do you have any other questions?
Can we Akbar 19?
19th, okay. 19th is 19th, which is not true. Okay.
Here
So
Maxwell Boltzmann distribution. What is that?
okay, so if you went through lecture 2, so for a given temperature, the velocities, so basically you see something, this graph, right?
Yeah.
This is Maxwell-Boltzmann distribution. So for a given temperature, you have the particles following a distribution of various velocities. Let's say you have 1,000 particles. All the 1,000 particles will not have the same velocity at a given temperature, okay, in a system. Some particles will have lower temperature, some will have higher temperature. So it is not single value, but multiple different values. But the average, if you take it, you will get the temperature to be just to a certain value. Okay. So that distribution is given by Maxwell-Boltzmann distribution. You can actually go through week 1 lectures. Sir actually taught in that. Okay.
Oh, okay, sir.
Okay. So that's it from my side today. If you have any other questions, we can discuss. Otherwise, yeah, that's it. Do you have anything else?
Number 3, can you answer? Can you solve this question one time? I have one answer, but this is
Which
some
which
problem.
question?
3.
3.
Yeah.
What? For an isolated system which has not reached equilibrium. That one?
I want 3.
Right. I'm sharing my screen. So question 3 is for an isolated system which has not reached equilibrium. The driving force for a spontaneous change is what? Correct?
Yes, sir.
Okay. So actually, important driving forces increase in entropy, but also there'll be a decrease in the internal energy, which is both potential and kinetic energy. So that is also a driving force. So this will be actually clear when sir teaches us Gibbs free energy. Okay.
Okay, sir.
All right, Jyoti. Anything else?
Okay, sir. No, sir.
Okay. So in that case, that's it from my side. So you can, leave the meeting.
Okay, sir. Thank you, sir.
Okay. See you. Bye bye. All right. So